48, okay. Here we go. Welcome to Physics X, Extraordinary Concepts in Physics, being taught at Michigan Tech, but available around the world. This lecture will be a 15-minute, there will all be 15-minute snippets on. This one will be distance scales in the universe 1, which means there will be distance scales in the universe 2 to follow. So it's being taught by me. I'm Robert Nemiroff at Michigan Technological University. So first, assuming people stumble on this and haven't seen anything else, where am I, what's going on? This is a course being taught on what I think are some of the coolest concepts in physics. It's concept-based and not math-based. It's referred to as Physics X, named after a course taught by Richard Feynman at Caltech several decades ago. It's being taught here at Michigan Tech for credit. It's aimed at upper-level physics majors. It's going to be light on math, though, and heavy on concepts, and anyone, anywhere is welcome. So if you stumbled on this, you're fine. We have no textbook required for this class. There are going to be Wikipedia links every lecture. They'll be the ones that are highlighted. There'll be other web links sometimes, and the lectures. That's all that's needed. Okay. So this lecture will be going through different distance scales in the universe, and we'll be talking about that next lecture too. So we'll go from the smallest size, supposedly zero size, to the largest size. Some of the smallest sizes are referred to as Planck scales, named after a famous physicist, Max Planck, who lived 100 years ago. So on the largest scales, we're going to have horizons. We're going to talk briefly, reviewing some things about things in between. Strings, elementary particles, life scales, cities, universes, metaverses. At the end of not this lecture, but next lecture, I'll be reviewing some movies that some people haven't seen. If you've seen them, I'm sorry. But the most famous one is called Powers of 10, which brings you through all the scales. So cool physics just brings you all through the different kinds of distance scales. Many times, strangely, the smallest and largest scales are connected in some strange way that people might not have guessed even 100 years ago. Okay, so I'll talk about fundamental units. So this is something I teach when I teach introductory physics. There are essentially 4 fundamental units in the universe. Now, many times when you take physics, you're given things like newtons and joules and things like that. And I remember when I was an undergraduate physics major, I would write things in those terms, but they didn't seem very basic to me. So the basic things you get to in physics are length, meters, time, seconds. Is just one way of measuring time. You can measure time in your own unit of time. You can Joe's time. It took 4 Joe's time to do something. But humans have decided that a second is something that we can all aspire to, all think about, oh, I know what that is. And then we have places like the National Institute of Standards that then define what a second is. So if we argue like, oh, that wasn't a second. No, I know what a second is, and this was a second. Then we can say, oh, how do you settle that? You go to a national or an international agency, and they will tell you how long a second is, how long a meter is, how much a kilogram is, and charge. So basically, you can describe anything. You can write newtons, you can write joules, you can write angular momentum units, all in terms of length, time, mass, and charge. Meters, seconds, kilograms, and coulombs. So for instance, acceleration would be just meters per second squared. Energy is just kilograms meters squared per second squared. So that's all these, it's deconvolved into these 4 basic fundamental units. Force, sometimes newtons, kilograms meters per second squared. Angular momentum, kilograms meters squared per second. And temperature, which is sometimes written Fahrenheit or Celsius or Kelvin, actually can be deconvolved per particle in kilograms meters squared per second squared. It's sort of a measure of speed of the particles. So I found this really useful when I was in introductory physics, because when I would have something on one side of the equation, one of the ways to make sure that I was getting something close to the right answer is to make sure my units were the same as what's on the other side of the equation. And the best way I found to do that is just reduce them to the fundamental units: meters, seconds, kilograms, and coulombs. Okay? So on to the next one. So in science, and particularly astrophysics, there are essentially 3 numbers that you have to remember. All those other numbers, you don't really have to remember them. First of all, you can look them all up on Wikipedia. They're all there. Second, but the way things work in science generally is many things are referred to as zero, that it had zero mass. For instance, many times, this is a controversial one, I'll hit controversy right off. Photons are always described as having zero mass. And you will find physicists who will just go crazy saying that you don't understand physics unless you know that photons have zero mass. But every time I say, well, what's an experiment that shows that? And they go, here's an experiment. And I say, well, that experiment can be turned around to put an upper limit on the mass of a photon, which means that the photon might not have any physically interesting mass at all. But it might have a mass. All we can do is put limits on it. And you can say gauge theories won't work, whatever it is. No, they would work within an approximation. Everything works within an approximation. But one number is it's too small to measure, like the mass of a photon. The size of an electron, it's too small to measure. We don't know. We don't know what the size of an electron is. We know a cross-section for it. We don't know the real size. So what we say when it's too small to measure, the way we say it is it's zero. That's what we say. Now, if we measured it, for instance, the distance between the Earth and the Sun, we can then say, oh, it could be some number of meters or kilometers. But many times, it's interesting to measure things in terms of other things. So many times you normalize it to 1. So the distance between the Earth and the Sun, you'll be happy to know, is 1. It's 1 astronomical unit. An astronomical unit stands for Earth-Sun distance. Infinity is very much like 0, and that's a common theme in physics and in math. 0 and infinity are convolved. So many things are too large to measure. Now we know the size of the visible universe, but past that, what's the size of the universe besides that? Don't know. We don't know. Nobody knows. It's too large to measure, so you can say it's effectively infinite. For all the equations, you just put in infinite and then terms drop out, that's fine. It could be in the future that things that are now thought to be infinite turn out to be measured. It's happened. Mass of the neutrino is something that's being debated. Okay. So objects with supposedly zero size, electron, quark, photon, graviton. Objects with size normalized to unity include the Earth-Sun distance. The Earth's radius is 1 Earth radius large. The Sun's radius. You can put 1 in terms of the other, but many times it's just convenient to just define it as 1. Objects of infinite size, the universe, something I think of as the gravitational horizon, where gravity works out to. The multiverse, so we'll talk about later in other 15-minute snippets of this lectures of this course, that there could be other similar universes to our own. And altogether, there's many ways to define multiverse. Okay, so now I'm going to jump into the world of Wikipedia here and go through orders of magnitude in length, for instance. So here we go. Let's hope the web is up. So the smallest magnitude length scale known is subatomic, and let's see, it's not scrolling down. So the Planck length, which we will learn a little bit about next time, is the smallest one that's commonly bandied about. It is typically a hypothetical size scale for a string in string theory, or M theory as it's sometimes called now. Length scales smaller than this become strange quantum mechanically, and we don't really understand how to deal with them. So 10 to the minus 35 meters is about as small as we're willing to go to measure things. Past that, you can put all these interesting something meter. There's all these prefixes to the meter. Let's see, a yoctometer, I see, is the effective cross-section of a neutrino with a certain energy. Now, do we really know the size of that neutrino? No, but we know that if we try to bang it into things, it's about that. You can roughly say it must be about that radius, or something is hitting with about that radius. There are things like attometers, and you move up. So that's the subatomic scale. Then you move up to the size of atoms. Most things are empty space, so there's the range of the weak force, which is 10 to the minus 14. The classical electron radius, which again, we don't really know the radius of an electron, but the interaction radius is 10 to the minus 15 meters. The Bohr radius of a hydrogen atom in the Bohr model is 10 to the minus 11 meters, and you can keep going up. Extremely ultraviolet light would be 10 to the minus 8 meters. Then you move up to the human scale, which is roughly a meter. So the average height of a human is given near here as roughly 1.7 meters. Average height of a human, 10 to the 0. Then you can get up to the length of the Suez Canal as 10 to the 5 meters, length scales on Earth. Then you get into astronomical scales, sizes of planets. The diameter of Jupiter, for instance, is, they moved into kilometers here. A kilometer is a megameter. 1,000 meters. So diameter of Jupiter is 100,000 kilometers. The diameter of the Sun is 1,000,000 kilometers. The distance that Voyager has gone is about 1 T-meter. I'm not sure, terameter, I guess. A parsec is, I guess, is a petrometer. Exameters. So you can measure sizes inside the distance inside the Milky Way galaxy, and the approximate size of the visible universe would be 100, I guess, Y meters. I don't know, is that Yada meters? I'm not exactly sure what Y stands for, but it's 10 to the 26 meters. Okay? So time scales vary dramatically too. So time scales go from, again, the minimum time scale that people are willing to discuss is the Planck time. It is essentially the time that we can track the Big Bang from. Earlier than that, not willing to really go there. We just don't know. Laws of physics as we know it don't really apply. Quantum mechanics applies in some strange way that we don't really know. Then we can move up to other fast time scales. Somewhere in here is the shortest period of time measured by a clock is 10 to the minus 18 seconds. Then you go up to your, I think maybe the global positioning system might be good to a microsecond or so. You can blink your eye in a millisecond. 1 second is a very common amount of time for humans. Then the time scale that glaciers move on might be best measured in eons, 10 to the 12 seconds, and the approximate age of the universe is about 10 to the 18 seconds. So that's the time scale for ages that people are willing to describe. Mass is a little bit different. Mass goes from, the lowest mass scales you see will be typically on the order of an electron volt, which is equivalent kilogram mass is 10 to the minus 36 kilograms. The lightest element, or particle, the electron, well, actually there's probably, who knows, the photon might have less mass than that. The graviton might have some mass. All we can do is put limits on it. The electron neutrino is down at around 10 to the minus 36 in terms of kilograms, effective kilograms. The electron is about 10 to the minus 31. Then you get into all different kinds of, like a water molecule is 10 to the minus 26 kilograms. Lead atom is 10 to the minus 25. The average human cell is 10 to the minus 12 kilograms. And you can go all the way up. Here's a good one. The dairy cow is about 100 kilograms. The International Space Station is 10 to the 5. And you go all the way up and through astronomical objects, most massive stars, clusters of stars, our galaxy all the way. So our galaxy is about 10 to the 42 kilograms, and the mass of the observable universe is about 10 to the 52 kilograms. You notice that we don't get into too many decimal places. It's just about that, which is good enough for this course. Okay, moving on to charge scales. There isn't very many charge scales. I'll clue you in on that. So the elementary charge an electron, which is about 10 to the minus 21, there might be 1/3 of that running around. There are 1/3 of that running around in quarks. Typically, though, you have to get macroscopic before you get higher than 10 to the minus 21 coulombs. So you get to the charge on a dust particle is 10 to the minus 15. That's pretty cool. I didn't know that. Power supply in your computer might have 10 to the minus 3 coulombs. A thundercloud might have 1 coulomb of charge in it. And the charge in your car battery might be 1,000. Okay, on to speed scales. So speed scales can go effectively to 0. We don't know a minimum speed. However, the rate of global sea rise between 1993 and 2003 was about 10 to the minus 11 meters per second. And the fastest speed, I'll skip along because I'm running out of time, is the speed of light, which is about 10 to the 8th meters per second. And there's lots of fun stuff in between, which brings me to, I think, the last one, temperature scales. Temperature is sort of like the average velocity of particles in a group. And so there is an absolute zero for free bodies that have a 0-point energy and no interaction with or without a thermodynamic system. And they can be at theoretically 0 Kelvin, which means we can't measure how low they can go. There are many other energy scales in between. The microwave background comes in at about, well, 3, about 1 in this 1 Kelvin. And things you see around you will be, let's see, a couple hundred Kelvin all the way up to, what's the highest? The Planck temperature of micro black holes evaporating are 10 to the 30th. So they can go really high. Temperature is a bit of a contrived unit, but it's something that's very fundamental that people are able to think about and understand in their own conceptual terms. So next time I will go through distance scales of the universe in a different way, talking about Planck scales and discussing a movie of these powers of 10 where you can actually see people's attempt to show a movie showing all these mass scales in a single movie. And I'll sign off for now and see you where you'll see me next time. Thank you.